but I'll just have a short request, which is if you could not upload the question section. Like the talk is fine, but the questions, if you cannot record that, or at least not
Okay.
put it up. Yeah.
The questions of the audience, if
Yeah.
that is it.
Yeah. Yeah.
Okay. Yeah, sure, sure. Should we start with an introduction or should we wait for 4 minutes or so?
Yeah. You can start whenever you want. I'm ready.
Okay. So, good evening, everyone. Today we have our last speaker as Debanjana Kundu. She is a faculty member at University of Regina. She completed her PhD from University of Toronto, Canada, and her research interests include diaphanted equations, Iwasawa theory, and beyond endoscopy. She will be speaking about Mobius functions today. Uh, Over to you, ma'am.
Thank you. So thank you so much for the invitation to speak and also for the very kind introduction. Um, and thank you to everybody who is attending my talk. So I'm going to talk about Mobius functions, and I understand that my audience might be a little varied in terms of your mathematical maturity. So if you're getting bored during some parts of the talk, I will have exercises for you to work on. And if this is all new stuff, you can take those as facts, right? For the purpose of understanding, knowing how to solve those exercises is not going to be important. So I hope everybody will get something out of this talk at least. And at any point of time, if you have any question, feel free to ask. It might become a little hard for me to monitor the chat. So if somebody who is kind of can just jump in and ask the question, I'm totally fine with that. Okay. So with that, let me start. I'm going to talk about Mobius functions today. And so when I give you the definition, you will realize it's a very, very simple function. And I will tell you about some properties of Mobius functions. And we will somehow link it to one of the most challenging problems, as I would like to say, in number theory. One is the Riemann hypothesis and the prime number theorem. So Riemann hypothesis is still a conjecture. We don't know how to solve it. The prime number theorem, on the other hand, is a theorem. We have known it for more than a century now, but it's still one of the probably highlights of analytic number theory. And I'm going to relate this very, very simple function to some facts and then talk about how it relates to these big ideas in number theory. Sort of also paving the way to say that, why is number theory so exciting and so hard? So hopefully everybody will get something out of this talk. And with that, let me start. So I'm going to start by talking about what is a multiplicative function. Okay, so let f be any arithmetic function By that, I mean it's a function that goes from the natural numbers to the complex numbers. This is just any function. I'm calling it an arithmetic function because it goes from um, n to c. And I'll say it is multiplicative if it satisfies the following property, right? So if m and n are two integers, which are co-prime to each other, and your function satisfies the property that f of m times n is f of m times f of n, then we say that the function is multiplicative. Okay, so let me give you some examples of functions, and I'll tell you which ones are multiplicative and which ones are not. Okay, so some examples are, let's say, tau of n. What is tau of n? It is the number of all natural divisors of n. So for example, if you take a prime number p, then tau of p is always 2, because how many divisors does a prime number have? It has 1 and itself. Now if you take p squared, it will be 1, p, and p squared, right? So for any natural number, you can say how many natural divisors does it have? That is called tau of n. And if n is, let's say you write down the factorization as prime 1 to the power of e1, prime 2 to the power of e2, so on up to prime r to the power of er, then tau of n has a very nice formula, which is product, let's say I going from 1 to r, e I plus 1, right? So it is e1 plus 1 times e2 plus 1, so on up to er plus 1. Um, so again, this, you can treat this as a small exercise. If you're getting bored, you can try to work this out. This is not hard. So then, just from the definition, and if you take this formula as God-given, you can convince yourself that this is in fact a multiplicative function. Okay. The second example that I want to give is sigma n. So what is sigma n? Sigma n is the sum of all the natural divisors of n. Right? So again, if I have a prime p, then what is the sum of all the natural divisors of n? I know that the natural divisors are 1 and p, so the sum is 1 plus p. Okay, if I have p squared, then it is 1 plus p squared. So again, if my natural number n is written as p1 to the e1 up to pr to the er, right, then sigma n has the following formula, which is again a product, which is I equals 1 to up to r, p I to the ei plus 1 minus 1 divided by pi minus 1. So again, you can think of this as a small exercise. And if you're finding this formula like too exotic, don't worry. Take small examples like n equals 4, n equals 10, and try to see how you might be able to manipulate the numbers to get this sort of formula, right? Um, and again, if you think of this formula as God given, then again you can check, or at least convince yourself that this is also a multiplicative function. The next example that I want to give you is what we call pi of n. And I understand this can be a bad notation because my product symbol and my pi is probably looking the same, but this is just standard notation in analytic number theory. So this is a capital pi. Don't think of this as product. I mean, this is not a product over all n's. This is a product function. This is the product of all natural divisors of n. So again, what would it be for something like the prime p? Well, the product of all natural divisors is just 1 times p. Or if you have p squared, then it will be 1 times p squared. So it's p cubed. And again, this also has a formula, but this will have a formula in terms of something that we have seen before. So pi of n is, in fact, n over tau n divided by 2. So it's square root of n to the power of tau n. And I will leave this bit also as an exercise if what I'm saying is a little boring for you. And you can convince yourself that this function is actually not multiplicative. Okay? So take a prime p and another prime q and see what happens, right? So you can take 2 and 3, or take something like 4 and 9 and see what happens, right? This function is not multiplicative. Okay, so we have talked about multiplicative functions. I have still not told you what's a Mobius function, so let me at least tell you what is a Mobius function. But before I do that, any questions?
Ma'am, shouldn't we tau of n by 2 GIF of it?
What? Sorry?
Shouldn't be the pi of n be n to d GIF of tau n by 2?
GI? Sorry, I can't hear you very
It's
clearly.
the greatest integer function of tau n by 2. The greatest integer less than or equal to tau n by 2. Like
The
the integral.
greatest integer less than or equal. You want the floor function?
Yes, yes.
I
So
That
don't think you need the floor function.
no, it works always.
tau of n can be odd, right?
If tau of n is odd, then n is a square.
Yeah, I think you'll be fine.
Ma'am, say for
Yeah, I'm pretty sure that this formula works.
Yeah, it's the right one.
Yeah.
ma'am, like with 10, it doesn't suit. Like with 10, tau of n is tau of 10 is 3, right?
Tau of n is 3. No, it's 4. Right? Because it's 1, 2, 5, 10. 10
Oh,
is a
okay.
divisor of 10.
Yeah. No, ma'am, 4, 4, yes. 4 should do that.
So you're saying 4. Yeah, but then n is 4, right? So when you do 4 to the power, so you don't have to think of it as, like, you can think of it as n square root n and then raise it to the power tau of n, right? So 4 is a square. So when you do
Oh,
square root of 4, you get 2. You can raise it to the power of tau of
yeah.
n.
Got it, ma'am, got it.
Yeah. Okay. But no, good questions. Keep them coming. So now the Mobius function. What's the Mobius function? So this is going to be a function that I'm going to denote by mu. This is an arithmetic function, so it's again something that goes from n to c. And how do I define this function? The definition is very simple. Okay, so I'm going to say mu of n can take three different values. It can be 1. Well, this is takes the value 1 when n is 1, right? So if the input is 1, I say mu of n is 1. If n is a product of distinct primes, right? So p1 up to pr, each pi distinct, then this is minus 1 to the power r. So if it's something like 5, if n is 10, then I have 2 times 5, so r is 2, and it will again give me 1. On the other hand, if I have 15, then it's 2 times 3 times 5, and then in that case, r is 3, and I'll get minus 1. And if n has a, if n is not square free, so at least one prime number that divides n comes with a power of at least 2. So if it's something like, let's say 4, or let's say it's something like 20, right? So it's 2 squared times 5. So there's a square part, so it's not square free. Then I say that my function takes the value 0. So this is a definition of the Mobius function. And if you are getting really bored during this talk, then I have an exercise for you, which is summation mu k. So you're summing k from 1 to up to n is less than or equal to n to the power of half plus epsilon for epsilon positive. I understand that this is not necessarily a question that many high school students would even understand, but if there's anybody who is maybe an undergraduate student in the audience and you want to take this question up as a challenge, this is totally fine. If some of you in the audience do not understand what is this epsilon positive, whatever, it's okay. This is not where this talk is going today. I just wanted to give a challenge to somebody who might be getting bored in this talk. Okay. So why is the Mobius function interesting, or why is it important? So one of the main reasons for this function being very popular for study is the following fact that I'm going to write down, and I'll give a quick sketch. So let's say I have summation mu d dividing n, then it takes the value 1 or 0 depending on n being 1 or n being bigger than 1. So what do I mean by this? So I'm given an integer n, and I look at all the divisors of n, right? So 1 and all the divisors of n up to n. And I look at the Mobius function of all the divisors, and I add them up, right? So that's what the left-hand side is. The claim is this is either 1 if your input function is just 1, and it is 0 if you put in any function, if you put in any integer which is bigger than 1. So how would you prove a statement like this? Well, I'm going to, again, like take a generic shape of my integer n. So it's going to be p1 to the e1 up to pr to the er. Okay. And now let's think about what does a divisor of n look like. So if d is a divisor of n, then D must be some P1 to the B1 up to some PR to the BR, where what are these BIs? These BIs can be anything between 0 and EI, right? So B1 can be 0. The divisor does not necessarily have a power of P1, but it can have everything between 0 and E1. All possibilities are okay. Similarly for P2 and so on up to PR. Another observation just from the definition is if for a divisor, any of these BIs are bigger than or equal to 2, I automatically have the Mobius function taking the value 0, right? Because it's not going to be square free. So if BI is bigger than or equal to 2, then mu D is 0. This is just by definition of a Mobius function. So I have made these very small observations. So now let me just write down what is summation mu D. So sum over all divisors of the function mu D is going to be R many sums. I'm just writing it down as one big sum of B1 up to BR of mu P to the power of B1 up to P1 to the PR to the BR. I've just written down the divisors as with its prime factorization. And now if I invoke the second fact that whenever I have BI bigger than or equal to 2, mu becomes 0, then what do I see? The only ones that can contribute are the ones which are which have a single power at best, right? So now this is a little bit of permutation and combination. So the first divisor is always 1. So mu of 1 is 1. And then if I have one factor in the of n or of an input, then it comes with a minus sign. And how many such possibilities do I have? I have r many primes, and I'm choosing exactly one prime, right? So this is minus r choose 1. Now, if I have two distinct prime factors, it's going to come with a plus sign. So it's going to be plus r choose 2. And you continue this up to minus 1 to the r choose r, right? You have chosen a divisor where all the prime factors are arising exactly once. And if you think about what does this mean, well, this is the same as 1 minus 1 to the power r. If you open up the brackets for, if you look at what is the shape of 1 minus 1 to the power r, it's exactly what I've written above. But what is 1 minus 1 to the power r? This is exactly 0. Okay, so straightforward proof if you just think about it a little bit, but this is going to be a very powerful statement. Or maybe another thing that I want to probably point out is a lot of calculations with Mobius functions sort of have this sort of a flavor in their proof, right? You just have to be sort of careful about which primes to include, and there's a little bit of combinatorics going on, but they're not necessarily very difficult proofs. Just take a little bit of practice. So now I'm going to tell you about two maybe like facts about Mobius functions, because I cannot go and prove everything because I want to get to something else. But let me tell you two more important properties or theorems about Mobius functions before I go more to the analytic number theory side. So the first theorem that I want to point out is called the Mobius inversion formula. And what does this say? So let's have two arithmetic functions, f and g. And my inputs are always non-negative, right? So let's say g of n is a function that can be written as summation f of d sum over all divisors of n. Suppose this is the shape of g. This is how I can define g. Suppose. Then what the Mobius inversion formula says is that you can write f in terms of g, but now you will have this Mobius function coming in. So this is again something that's used a lot when you're sort of working with analytic techniques. So then f of n can be written as summation d dividing n mu of d g n over d. So now what's coming inside the sum is the Mobius function of the divisor, and the input value for the function g is what you get when you divide n by d. And then you're summing over all the divisors of n, that gives you fn. That's called the Mobius inversion formula. It's sort of allowing you to go between g and f. And the Mobius function plays a very crucial role here. And there's a multiplicative version of the same Mobius inversion formula. So now if your function, so it's the same sort of a setup, you have two arithmetic functions, f and g. Input values are all non-negative. Suppose you can write down gn as product over all divisors of f of d. So now you have another function f, but you're writing g in terms of the product of the input values of f of d, where d is dividing in. Then, as you might expect, I can write down f in terms of g, but this formula will involve a product. So then f of n is product d over n, oops, not d over n, d dividing n, mu, sorry, it's g d mu to the n over d. Or you can write it as g n over d to the power of mu d, right? Notice that if d divides n, then n divided by d also divides n, right? So why did I tell you this? Because I want to relate another very commonly used arithmetic function in this way. So this is a function that maybe most of you have encountered already, or at least many of you might have encountered this. This is called the Euler-Totient function. What does this one do? This is the number of positive integers less than n that are co-prime to n. So we denote this by phi. This is the number of positive integers less than n that is co-prime to n. So let's say you're looking at the prime, you're looking at the integer 5. What is the Euler-Tauschen function for 5? So 1 divides 5. Well, okay, sorry. 1 is less than 5. It's co-prime to 5. 2, 3, 4. So everything before 5 is co-prime to 5. So phi of 5 is 4. Now let's say you have the number 10. So 1 is still going to be counted. 2 and 10 are not co-prime, so I don't count 2. 3 will be counted. 4 will not, 5 will not, 6 will not, 7 will be counted, 8 will not be counted, 9 will be counted. So phi of 10 is also 4, right? So this is the Euler-Tauschen function. And again, if you are interested, you can try to show that sum of phi d dividing n is exactly equal to n. So otherwise you can take this as a fact for now, but there are several ways of proving this. But if you're interested, you can try to prove it. Otherwise, let's just take this as a fact. So why did I give you this formula? Because I want to relate this to the Mobius inversion function, right? So my function here, right, n, this is like the identity function. So g of n gives you the output n, right? It takes in whatever integer, spits out the same integer. It's an identity function, very much an arithmetic function. And I'm writing this as a sum of phi d as the sum runs over the divisors of n. So phi of d is like my f of d. So I'm writing n as summation of an arithmetic function. So I can apply the Mobius inversion formula. So by Mobius inversion formula, I have that. So what does it say? It says phi of n can be written in terms of g, which is my identity function. So phi of n is summation where the sum goes from over the divisors of n, Mobius function times g of n over d, but my g is just the identity function. So this is n over d. And if you want, you see that the sum is running over the divisors of n. This object n does not really depend on d, so you can pull that out of the summation and say that phi n over n is summation mu d over d. So d divided. Okay. So this is coming from the Mobius inversion formula. Maybe one more function that I want to introduce is the omega of n. So when you're working with multiplicative functions as a whole, right, not just the ones that I've talked about, what is just very common is because you know that it's multiplicative, so its values will just depend on, you can look at just prime powers and talk about them separately. You just have to kind of think about the prime powers that are showing up for each of the primes. If you have two multiplicative functions that agree on the prime powers, then they'll have to agree everywhere. You don't really have to check at every integer. for example. So you just restrict your attention to studying prime powers, and that's good enough. So just to sort of give another flavor is so if you go back to the mu function, right, the Mobius function, you notice that it can take 1, -1, 0. It can take these three values. But if you take the square of the mu function, then it's going to take either 0 or 1. So it's some kind, so mu square is some kind of an indicator function, right? Because it says yes or no. So it's indicating something. But what is it indicating? Mu squared d is the indicator function for square free numbers, right? If it is, so if the number is square free, that means no prime power appears as a square or higher power in the prime factorization of n, then it'll give you a yes, it'll give you 1, and if any integer, if any integer has a prime factorization and it is square full or not square free, then it's going to give you 0. It's going to give you no. So it's an indicator function for understanding whether a number is square free or not. So let me give, you can think of it as an example, you can think of it as an exercise. So mu squared d, so this just means mu d times mu d, right? So you can think of it as mu d squared. I just like to write it this way. So mu squared d is an indicator function for square free numbers. And what do you get when you're summing over mu squared d's, d dividing n? So again, if your n is more like if your d has a square, if your d is not square free, you're going to get zeros. You only have to look at whether a prime shows up or doesn't show up in the factors. And if you're summing over all of them, this is just 2 to the power of omega n, where I'll tell you what omega n is. Yes, absolutely. It is 2 to the power of omega n. Very good. So what is omega n? Omega n is the number of distinct prime factors of n. Right, so right, so let's say my integer is 10, right? So there are two distinct prime factors, 2 and 5. On the other hand, if basically that's exactly what it is. But if you have, let's say 20, then you have 2 squared times 5, but the number of distinct prime factors is still 2, right? 2 and 5. Sure, one prime factor is appearing more times, but that's not relevant. So mu squared d, or sum over mu squared d for n 10 or 20, if you believe this formula, is exactly the same. Okay. And again, it's a fairly easy thing to check and convince yourself that omega n is also a multiplicative function. Okay. Sorry, not omega n. 2 to the power of omega n is a multiplicative function. Omega n is not. Okay. So why was I telling you so much about Mobius functions? I said I wanted to sort of tell you about its connections with Riemann hypothesis or the Riemann zeta function. So before I can give you the punchline, I have to like again build up some notation, build up a little bit of vocabulary. So we will take a short break from talking about Mobius functions to talking about what's called a generating function, and then I'll tell you about the Riemann zeta function, and then sort of build the connection. So, what's a generating function? So I will not need like the full force of a generating function per se, but I think it's still a good way to motivate what I want to say. So if I have a series, this is an infinite series. So I'm going to, sorry, this is not n bigger than or equal to infinity. This is n bigger than or equal to 1. So I'm starting, you can start from 0. It doesn't quite matter. So I'm summing over 0 or 1. I'm going to sum over all integers, right? So whatever I'm going to write down inside, it's going to take values n equals 0, n equals 1, n equals 2, up to infinity in some sense. This might be disturbing for some people in the audience. As mathematicians, we do it formally. So this is an x to the power n. So this is a series. X is some variable that I don't care about right now. So the series just means a0 x to the power 0. So that's just a0 plus a1x plus a2x squared plus a3x cubed, so on. This is an infinite sum. And if I can write this as some function of x, then I call fx as a generating function. So when I say it's a function of x, I'm not writing it as a sum. I'm writing it as a function as you sort of understand it, right? So this is a yeah. So on the left-hand side, I have a formal power series, and on the right-hand side, I have an honest function. This will be called a generating function for the sequence a0, a1, so on. Okay, so again, this might be a little disturbing for some, so let's do a very, very quick example. So I'm sure everybody in the audience knows what's a Fibonacci number, right? You start with 1, so that is f of 0, we say is 1. We fix f of 1 as 1, and then everything after that is defined as the sum of the previous two numbers, right? So f of 2 is 1 plus 1, that's 2. F of 3 is f of 1 plus f of 2, so that's 3. F of 4 is f of 2 plus f of 3, that is 5. And after that, I'm going to confuse myself just because I'm speaking. But this is how a Fibonacci number works. So I can think of so I have a sequence of numbers, right? This will go on till infinity. So I can think of f n x to the n. So I have this infinite series. And I want to write down what is the generating function for f of n. So how will I do that? So I can start sort of thinking about, let's write this down formally. This is 1 plus x plus 2x squared plus 3x cubed plus 5x to the power 4 and so on. I'm going to write down something in the next line which requires a trick, and I'm going to leave that bit as an exercise. You should convince yourself that you understand why that statement is true or why this equality is true. But this can be written down as 1 plus x plus x squared whole squared plus x plus x cube. Sorry, x plus, no, this is not correct. Give me a second. This is 1 plus x squared, 1 x plus x squared squared, so on and so forth. And then you somebody wrote down something in the chat which is a little wrong because I'm starting from n equals 0. I think what you wrote down will be correct if you write if you start from n equals 1, but that's okay. So now this is an infinite sum, so you can sort of, I haven't been very specific about convergence and stuff, but you can assume that x is yeah, very good. But you can sort of assume that x is small and there are no convergence issues. You can do that, and then you get 1 over 1 minus x plus x squared. This is just like an infinite sum, so more like yeah, your GP calculations, your geometric progression calculations in some sense. And then this is basically what was written down in the chat. This is precisely 1 over 1 minus x squared. And if you start from n equals 1, then you have a factor of x at the top. So again, you can start from x equals 1. There's nothing wrong with it. Sorry, from n equals 1, there's nothing wrong with it. I just started from n equals 0. So in this case, the generating function for the Fibonacci numbers is this function, 1 over 1 minus x squared. Okay. Why am I telling you all of this? Because I'm going to tell you about the Riemann zeta function, which will be, in some sense, like the generating function for the Mobius function. So what is the Riemann zeta function? This is a function that has the following shape. S is, to be very precise, it can be any complex number as long as the real part of the complex number is strictly bigger than 1. If you are not familiar with complex numbers, think of it as any positive number, positive real number, which is bigger than 1. Otherwise, you will have convergence issues, which we want to avoid. You can make sense of this S to be any number on the real line. Why is that true is a deep fact about what we call analytic continuation. But for the sake of the definition, think of it as any number that is strictly bigger than 1, but know that you can make sense of it even for numbers which are less than or equal to 1. Okay? Yeah, so the formal condition is the real part of S is strictly bigger than 1. That is the formal way of writing the Riemann zeta function. But what is this function? This is summation 1 over n to the power s, where you're summing over all n, bigger than or equal to 1. So I have fixed a function. I fixed an integer s, let's say. Let's say I fixed s is equal to 2. Then zeta 2 is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. Okay? This sum is actually a finite number. And you can actually rewrite this sum, and this is actually a fun problem in combinatorics. You should think about how you might be able to prove this, that you can write this as a product over all primes 1 over 1 minus p to the power of minus s. So again, why is this equality true is not important for today's talk, but the definition is this summation, but you can rewrite this and write it as an infinite product over all primes. Okay, and I don't want to go into a lot of details, but using some complicated functions, which involves the sine function, there's something called the gamma function, you can actually relate zeta of s. P is any prime. So for me, P is always a prime. Okay? So zeta s can be written as zeta s and zeta 1 minus s can be written in terms of each other. And there's just like some very complicated functions that relate them. And something that one can show with a little bit of analytic number theory is, as I said, the definition makes sense only on the right hand side of the of 1, but you can, using this relationship between zeta s and zeta 1 minus s, do what's called analytic continuation and extend it to the left of 1. And what the Riemann hypothesis is trying to say is, well, zeta at negative integers, zeta of minus 2k for k an integer, is always 0. Okay, this is coming from analytic continuation that I will not talk about today. This is not the audience to talk about analytic continuation, but you can make sense of it. This is always 0. And what the Riemann hypothesis tries to answer is, where are the other zeros of this function? For what other values of s will zeta take the value 0? Of course, you understand that if I'm summing only over like on the right hand side, I'm probably never going to get zeros, right? Because this is just summing positive numbers. But as I said, this is s can be any complex number, right? So s is not just a real number. S can be any complex number. So asking for where does this function become 0 is a legitimate question. So how do I relate zeta to mu? Why was I talking about mu? And then why did I start talking about zeta? Well, that's because I can write down 1 over zeta s, right? So now I've just taken the reciprocal of my zeta function. That is product over all primes p, 1 minus 1 over, actually, this is not product over. Yeah, I mean, I can write it as product over all p, but I think I want to write it a little differently. I want to write it as a product over all k, but I'm writing my primes as pk, right? So p1, p2, p3, they're infinitely many primes. This is the same thing as I've written above, except that I think I made a mistake here. This one should have had a negative 1. Okay, so I have my 1 over zeta. No, p is not a fixed prime. P is varying, right? So this product is over all primes. The sum the sum is over all integers n. So here n is any integer, here p is any prime. Does that answer your question? Okay, so, okay, perfect. So now I'm writing down the same thing as I've done before, but what I'm saying is I'm just not going to write it as products of primes, which would have been totally fine. But the way I'm writing it is I'm calling the primes P1, P2, P3, so on, and I'm saying I'm taking a product over all k. K is, again, any integer, right? So P1 is a prime, P2 is a prime, Pn is a prime. So now if I break open this prime, if I break open this product, what is it? It is 1 minus 1 over P1 to the s times 1 minus 1 over P2 to the s, and so on. Now, if I do this product, see that it becomes 1 minus 1 over P1 to the s plus 1 over P2 to the s, so on. So every prime is showing up exactly once in the denominator, plus 1 over P1s, P2s, plus 1 over P1s, P3s, so on. And then you'll have, I mean, this is probably very, very concerning for some people, but these are all infinite sums, and we have made definitions in a way so that convergence issues don't happen. So this is legitimate, believe me. So what's showing up in the first bracket is denominators where only one prime appears. What is showing up in the second bracket is denominators where exactly two primes appear, and so on and so forth. And you can continue doing this when you open up the brackets in the first line. And if you think about what have you done, well, this is 1 minus summation 1 over pi to the s, where I is bigger than or equal to 0, plus, this is just, again, a formal way of writing down what I've done already. Oh, well, not I equal to 0. This is 1 over pi s, pjs, and then so on. But this is precisely, if you think about it, again, believing that convergence is not an issue, you realize this is precisely mu of n divided by n, sum over all n. Because every time, because any n will be showing up as a product of primes as above, n to the power of s, right? This is just prime factorization. So every integer shows up in that sum over here, and you can therefore, and the mu that you have is the number of prime factors, which is positive or negative to the power of r. So this is precisely mu of n to the power n over s. I will be done in like maybe 2 more minutes. You have a question?
Ma'am, shouldn't there be a negative sign in the second statement at the last?
Yeah, of course. This is like just, yeah, the
Alternating
next one.
signs.
Yeah. This is alternating sums. Perfect. So this is, so what I want to say over here, the reason why I did this calculation is this is not exactly like a generating function, right? Because if I had a series, I wanted to write it as anx to the power n, and this is not quite that shape, but morally this might look like a generating function. So in some sense, from the definition of what I told you is a generating function, this is not an honest example of a generating function, but morally, what one can say is 1 over zeta s is something like a generating function for the Mobius function. Okay, so you understand that this really complicated object, which was zeta function, which I was having trouble explaining without going into a lot of details about complex numbers and, you know, analytic continuation and everything, is a generating function for this very simple function, mu of n, which just takes 3 values, right? 0, 1, or -1. So this sort of shows a very, very deep connection between two very different looking functions. And the last thing that I want to leave you with is, okay, so I have mu of n to the divided by n to the power s. Let me say s is equal to 1.
And what
So
was
n is always just any integer, positive integer.
any positive integer?
Yes. So I'm summing over all n.
Okay, got it.
So now if s is equal to 1, what do I have? I have summation mu n divided by n. So if I just think about, I know the definition of mu of n. So let me try to think about what does this sum look like. So mu of 1 is 1, 1 divided by 1. Mu of 2 is -1 because 2 is just one number, 1 prime. So mu of 2 is -1 divided by 2. Then I have mu of 3, which is again minus 1 over 3, so on. Well, mu of 4 will be 0 over 4. Then I'll have minus 1 over 5 plus 1 over 6, and so on. What does this sum equal? The way I want you to think of this sum, this might look like a little scary, but the way I want you to think about it is, let me start with all the numbers. If you want, you can think of all the numbers in some very large interval. You can fix like a capital N, like 1,000,000, 5,000,000, 200,000,000, whatever. And then you'll have to take n going to infinity. But okay, you have all the positive numbers. So these are all the numbers. The ratio is 1 over 1. Okay. Now I want to remove all the even numbers. So I have removed half of them. That's the minus half. Now I want to remove all the numbers that are divisible by 3. Okay. So I've removed all the even numbers. I've removed all the numbers that are divisible by 3. But that means I have removed the numbers that are divisible by 6 twice, right? So I want to add those back. So that's why I have a plus 1 over 6. I'm not doing anything to the 4. So I basically want to now look at 5. 4 is not a prime number. So that's why I don't care about 4. Now I want to remove all the numbers that are divisible by 5. But then I would have removed numbers that are divisible by 10 twice. So I'll have to add that back. I would have removed numbers that are divisible by 15 twice. So I'll have to add that back. But then numbers that are divisible by 2 times 3 times 5, that's 30. Think about it. How many times have I added and removed them? You will realize that I have one extra factor of 1 over 30. So I have to remove that. So I'll keep doing this sum. So what am I doing? I'm trying to remove these numbers, like one product, like one prime factor at a time. And as somebody correctly pointed out in the chat, this is exactly 0. Okay? So again, a very complicated looking object, but sort of you can make sense of it in a combinatorial way to say that summation mu n over n, when I'm summing over all integers, is always 0, or at least converges to 0. And what I want to leave you with, the final statement, without any proof, is that this statement, which at least, verbally can be explained, not super rigorous, but you get an idea of where this is going, is equivalent to the prime number theorem. What is the prime number theorem? The prime number theorem says that if I have a very, very large number x, like say 200 million, 500 million, 700 billion, whatever, if I have a very, very large number x, the number of primes up to that number has the following shape. Prime number theorem says, so as mathematicians, we run out of letters very quickly. So this is also called pi of x, but this is little pi. So this is the prime counting function. So this is how many prime numbers do you have up to a large number x. This is asymptotic to, this is not equal, right? I'm not saying this is exactly going to be equal to this number, but it's going to be close enough to this number, which is x over log x, right? So x over log x is not even an integer, so you can understand this cannot be an equality, but this is how fast that function is growing. But this summation mu n over n being equal to 0 is exactly equal, or is equivalent, I should say, to counting the number of prime functions, counting the number of prime numbers up to a large number x. Why is this equivalence true is, again, not something. That's a very good question. I'll tell you what that means in a second. So this is not something that I can talk about in this talk. This does require a little bit of more advanced analytic number theory. But again, my whole point was to sort of explain to you that, some very simple things can be related to some very complicated looking things. And hopefully this is going to be this will be inspiring for some people to continue studying number theory. Okay, so there are a couple of questions